Okay, so we spent the last couple of lectures talking about classical mechanics, and I paid a lot of attention to the fact that you could reformulate classical mechanics not in terms of actions and branches and rate of motion, but in terms of the Hamiltonian. Their equivalent formulation, except for the fact that the Hamiltonian equations of motion are first order, whereas the Lagrangian equations of motion, the Lagrange equations, are second order. So if you want to solve differential equations, then it's obviously easier to work with first order differential equations than second order. But there's something deeper going on in the Hamiltonian formulation. And that deeper is related to the fact that the Hamiltonian formulation, well, it's related to the fact that the phase space in which the Hamiltonian formulation takes place is an example of what we call symplectic manifold. And symplectic manifolds and the symplectic structures that are developed, defined on such symplectic manifolds are a really beautiful example of how the language of differential geometry allows you to extract some of these physical consequences in a really pretty way. So I want to explore a little bit of that today. So what we're going to do is revisit things that we've been talking about in the last couple of lectures and frame them in the language of the differential geometry that we've been building today. Okay. So first I should tell you what, so this is just a last, I mean, this is still part of this example that I'm doing on classical mechanics. But it's the last part of the differential on this. So this lecture will tie this up. And in the next lecture, we'll start talking about integration on manifolds. Speaking of which, I need to run something by you guys. I have a meeting that still needs to be confirmed, but that I can't really get out of on Friday. And we've had a lack, it's not a lack of well, April's like one big holiday, right? Just dispersed with a few days of work here and there. So it's my lectures happening on Monday, Wednesday, Friday, very hard. So what I would like to propose is if we can do the Friday lecture online. Instead of in person, so that way I can do it at a slightly different time, like 12 o'clock maybe. Or if it's possible, if we could do the Friday lecture at 12, that would be great too. Could we do that? Does anybody have any objection to running the Friday lecture at 12?
In here or online as well?
I'm sorry. No, in person. So I can make it 12. I can make it at 12. I think the meeting goes like 11 o'clock at 12. So I can make it at 12 o'clock in person. Otherwise, I'll have to do it online. So if you guys can make 12 o'clock, I can be in. All right. Thanks for giving me an excuse for walking out that meeting. All right. So let me tell you then what a symplectic manifold is, a symplectic structure that defines a symplectic manifold, and how this is all tied into classical mechanics. So the idea here is that the phase space that we've been talking about is the space parameterized, coordinatized by generalized positions and generalized momentum. Okay. So phase space is an example of a symplectic manifold. So by way of definition, a symplectic manifold is any manifold that is equivalent to a symplectic structure. Sounds kind of secular. So let me tell you what a symplectic structure is. A symplectic structure is a particular type of two-form. So if I give you a space and there is a particular two form or the symplectic form defined on that space, then that two form constitutes what's called a symplectic structure for that space, and it makes that space a symplectic manifold. So a symplectic manifold is any manifold equal to the symplectic two form. That's it. So what is the symplectic two form? Well, a symplectic two form is a closed, non-degenerate two form. That's it. So I need to find a closed, non-degenerate two form. We know what closed is. I'm going to tell you what non-degenerate two form is just now. But if I can find any such closed, non-degenerate two form on the space, right, on the space of two forms on the manifold, then I say that that manifold is symplectic. Okay. So a symplectic form or symplectic structure is a closed, non-degenerate two form omega will be half omega mu yes mu which yes mu. That's it. So closed here means that E omega 0. Okay. Take the exterior derivative of the form that is closed form, then that exterior derivative will vanish. Non-degenerate here means the same as you would expect non-degenerate to mean in the matrix sense. I have a matrix of coefficients here, omega mu nu. And non-degenerate two form means that this matrix must be non-degenerate. What does a non-degenerate matrix mean? In the linear algebra sense.
That's eigenvalues. The eigenvalues.
Something what?
The eigenvalues.
Not necessarily, but invertible. It means that it's an invertible matrix. It means that the determinant of this matrix of u that u is not valid. So this means that omega mu is an invertible matrix of coefficients, which is equivalent to a statement that the determinant of omega mu or the matrix is not 0. But there is also a sense in which this two form is non-degenerate, and I don't need to specify some matrix of coefficients in some coordinate basis, right? So the whole point I'm trying to evade in formulating everything geometrically is that I don't need coordinates all the time, right? So this is a coordinate definition. I pick a set of coordinates, I can write this two form in that set of coordinates. I have some matrix of coefficients. My statement is that this thing is a non-degenerate matrix. Sorry, this thing is a non-degenerate two form if the matrix of coefficients is non-degenerate, which means that it's invertible. But let me give you a definition that doesn't involve picking a set of coordinates. So in this case, non-degenerate means that, remember, this guy here is a map from the set of, it takes in two vectors and it chucks out a number. Okay, that's why it's a two. So non-degenerate omega is non-degenerate. Yes. And only if omega of x and y, the vector field x and y equals 0 for any vector y in tangent space manifold FFP implies that X at P certainly got it. They're equivalent statements. This is an equivalent statement to having an invertible matrix of coefficients. So you can check by picking a set of coordinates and showing that this is true. So it's a non-degenerate matrix if and only if omega acting on two vectors x and y is 0 for all y in the tangent space, and P implies that x at P is also equal to 0. All right. So that defines for us a symplectic two-point. My statement is, if I can find a symplectic two-point on the manifold, then it equips the manifold with the symplectic structure, and that manifold is then a symplectic manifold. So a symplectic manifold is any manifold equipped with a symplectic structure. Symplectic manifolds and symplectic geometry on symplectic manifolds is a really beautiful subject that is relatively new in the space of people exploring differential geometry. So there's a lot that's still to be learned about symplectic manifolds, and that contributes back into classical mechanics, and classical mechanics feed back into more and more geometry. So this is a really, really active area of research in geometry at the moment. And I strongly urge those of you who are so inclined to follow up on what's being done in this field as well. Okay. So let's return to our story now and ask if we can formulate classical mechanics, Hamiltonian classical mechanics in this language. Right, so what do we need where are we going? We're going to find, hopefully, a coordinate-free expression for Hamilton's equation. If I can do this, that will be enough. Turns out, one of these, you call in the next 2 hours and get something free. We'll find that in formulating Hamilton's equations, we'll also be able to formulate, give a coordinate-independent definition of the Poisson brackets. So we're going to be happy with that, and we'll move on to integration. But again, really active research area. Strongly urge you to follow up should you some inclined. Okay, so suppose I have a Hamiltonian. So Hamiltonian is a function defined in the space space. It's a function of the Q mu's and the P mu's. Now, there's one point that I need to make here, which is that I know, you know, I know that you know, that momenta and generalized coordinates are not the same thing. They have different units and they transform differently under coordinate transformations. But in this context, I am using them to coordinatize a manifold. So depending on the textbook that you're looking at, some people define it differently. I'm going to choose a particular definition of what the space-based coordinates look like. I'm going to stick with that definition, and I'm going to, anywhere there's a conflict, I'll tell you about it. But you might encounter other texts. Nakahara, for example, uses upstairs and downstairs indices for the Q mu's and the P mu's, as one should, because they are different objects. But when you start doing that, then you start writing the coordinate basis for forms with indices downstairs, and that tends to be a little bit confusing. So I'd like to stick with our definition of forms, which the coordinate basis for a form has its indices upstairs, unlike the coordinate basis for a vector, which has its indices downstairs. The indices for the components of the form are downstairs. That's what we've been using consistently. I'm going to stick with that. So for that reason, I'm going to write down the p-values with indices upstairs. Again, I'm very familiar with the fact that the indices really should be downstairs, and I've been using the notation a little bit to be consistent with this. Right? If I stick with the fact that the indices should be downstairs, then we'll start writing things with forms of indices downstairs. And I prefer, it's a give or take, and I prefer to stick with this as being consistent. Right? So suppose we have a Hamiltonian defined on a phase space. It means that this thing is a function of generalized coordinates, Q and generalized momenta, Q. This is what I got, right? So normally I would have to write that as Q the new classes. So make a note here, just in case of what I said. Okay. So given this Hamiltonian function on the phase space, and again, let me just recap what I said about phase space. If I have a classical mechanical system with n degrees of freedom, that means that there are n such q's, u goes 1 to n. Then phase space is a 2n dimensional number. Okay, because it's coordinated by the generalized position and the generalized momenta. Okay, so I can define a velocity field, velocity vector field, generated by this function. The velocity field generated by H is defined to be x sub H, and it's basically this following notation that we would normally use to talk about velocities and tangent vectors. Q dot means derivative with respect to some parameter t, say, d by dq plus E mu dot d by d p in. Generalized velocity field, the velocity field generated by the Hamiltonian, this guy, and it's found by solving the equation dh equal to minus the interior product of omega with respect to the velocity vector field. So again, remember the interior product is a contraction. This guy is a form. If I contract the vector, it should be in one form. This guy is a function. If I take the exterior derivative, this is the one form. So everything is sanity check what's up, right? One form on the left-hand side, one form on the right-hand side. This minus sign is convention. It depends on how you define the two form. We're going to define the two form, specific two form, the specific symplectic two form in a particular way. We'll bring this minus sign. Some authors define it in another way, which will absorb this minus. So just be aware that this minus sign is convention. So this is a one form. This is a one form. Again, this is a two form because the symplectic two form manifold. Are there any two form? So again, I have a manifold. It is a symplectic manifold. It's put with a symplectic structure. This closed non-degenerative. Okay. I start off with my Hamiltonian vector field. Sorry, I start off with my Hamiltonian function on that first space. I define a velocity field associated to that Hamiltonian. It's a velocity field generated by that Hamiltonian. That's what it is. So basically, I take the Q's and the P's and I write down Q dot, P dot, D by dQ, D by dQ. Okay, so this is a vector field. I then take the interior product. So I contract the symplectic two form with the velocity field, and that'll give me a one form. Up to a minus sign, that one form is exactly equal to the exterior derivative of the Hamiltonian function. So this is a differential equation. And if I solve this differential equation, this is the result of that. All right. So the velocity field is comes, if you want to know what the velocity field is, it is the solution of this differential equation. Again, this here is conventional. Sometimes you'll see it, sometimes you won't, depending on the theory. So let me show you that this equation here, equation 3, is nothing but the Hamiltonian equation we discussed. Right? So if I can show you that that's the case in a particular coordinate, right? This here is a coordinate invariant formulation of the Hamiltonian equations. I don't have to tell you anything about coordinates. When I do pick a set of coordinates, we will demonstrate that now. When I do pick a set of coordinates, this will be the Hamiltonian equation. But I don't need that set of coordinates in order to tell you what. So this is a coordinate independent definition of the Hamiltonian equations. Right? It's purely geometric. So let me show you if that is the case now. So to do that, I'm going to define plane elements. Equation 3 is nothing but the Hamiltonian equations of voltage associated to this particular Hamiltonian. Right, so let's show this. So to show this, I'm going to pick a particular coupon. Or let's say choose. I'm going to choose the symplectic coupon to be G, P, mu, wedge, G, Q. And here I really need to sum over the mu's. Right? So there's more mu's notation. I told you the last time we will sum over Greek indices if they're one upstairs, one downstairs. So technically what I mean is sum over mu equals 1 to m. Okay. So I'm going to choose my symplectic form to be this. And I want you guys to check that this particular choice satisfies the fact that it's a symplectic form. So d omega is 0, kind of obvious, but that this definition holds as well. Okay. So what I mean here is the P1, which the Q1 plus all the way through to the N, which the Q. This minus sign story that I was telling you about is now some locals define omega as dq where dp. If you define omega as dq where dp, there's a minus sign that's not flipping these two, and then the Hamiltonian equation is just dA equals I sub x omega. Okay. Nakahara Frankel, all define it this way. I'm choosing to stick with this way because it's more people do it. Okay, so let's show then that gradient P is just so on the left-hand side. Left-hand side of gradient P in this quarter basis is DH. And if H is a function of P's and Q's, then DH is DH by D Q mu D Q mu, thus DH by P mu. In P mu, this is the chain rule applied to this function. So nothing deep about that. On the right hand side, on the other hand, we'll have the forms. So forgetting about that minus sign for now, we'll fill that in at the end. The interior product of omega with respect to the velocity vector field is d p mu with d q mu at two form omega acting on the vector field. So q is in mu dot d by the q mu plus p mu dot d by the p mu. Technically, the two form and it takes in two arguments. So I should separate this. Something like that. But this is just p mu dot dq mu minus, so that's this term here I get by acting this on this. Okay. And then this acts on this, but I need to exchange these two so that the q's are in front of the p, that comes from minus sign. That's q mu dot dp. So please make sure that you're comfortable with this action. So put in the details there. We've done this a couple of times already with the action with the interior product. But then I get to compare this thing up to a minus sign with that. So let's start in the minus sign and then the minus plus. So now I can compare this with this. So comparing coefficients. I'll find that this term is this. So that's q mu dot is dh by dp mu and p mu dot is minus dh by dq mu. Again, this is nothing but the Hamilton equation one. Okay. So the point here is that to get this form of the Hamilton equation motion, I had picked a set of I had picked a set of QUs and PUs, generalized coordinates and generalized momentum space, and pick a particular form for the symplectic form, and then I can show that this is true. But this here is a coordinate independent statement that is equivalent to this. This is the coordinate independent. This is the strictly geometrical statement of the Hamilton equation. Now, there's a caveat to the story. It sounds too good to picture. And the caveat is that there's something called Darboux theorem. Darboux theorem tells us that locally, any point of the symplectic, I can always use this. I can always pick a set of coordinates P mu and X mu, sorry, P mu Q mu, such that the symplectic two form can be reproduced. So, if you're critical of this story, then you would say, what's the point? If there's a theorem that guarantees that I can always pick this set of coordinates locally, then why do I need this GH equals minus I omega? Why do I need a coordinate independent statement if I can always pick local coordinates? Anybody has a guess as to why you would bother going on after this and after this slide? That's it. Yeah? Because local is the key word in that statement. Darboux theorem is a local guarantee that you can pick the coordinates. It doesn't say anything about what happens if these coordinates overlap. Right? So the thing is, I can always define a local neighborhood of some point. So I start off with some point, a P. Locally, I pick let's say X. Locally, I pick some set of coordinates P and Q. Right? And then I can do all of the stuff that I'm working with Hamilton's equation in the form that you know in logarithm. Right? This guy, on the other hand, is independent of what set of coordinates. So it means that if I take another point, X prime, that's close to this point, use Darboux theorem there, get local formulation here. In this overlap of these two regions, right, I have a transition matrix. And the transition matrix has a property that it mixes up P's and Q's. So what you were calling momenta in the one set of coordinates will become a mixture of momenta and position in the other set of coordinates. Right? So now I'll try writing this local set of equations, and it gets horribly mixed up. Okay. However, this guy stays in there. That's the power of this geometrical way of thinking, right? When you get measured with coordinates, and for those of you that have done general relativity, you know exactly what I mean. When you get measured with coordinates, you really have to keep track of things because the transition function will mix them up, mix up your definition of what is momentum and what is coordinates in the overlap. This is your guide. This is always true. Okay, so that's a caveat that that one needs to keep in mind as one goes along. So let me state this so if anybody wants to follow up. Because Dr. was French, you only pronounce half the word. The Darboux theorem guarantees that locally always gives but when P is true low, so there's a couple of points to note about the symplectic form. Some properties of the symplectic form. Include the following. One is that symplectic form is invariant along the slope generated by the vector field, velocity vector field. So what I mean by this, omega is invariant along the slope generated by the velocity vector field. So that means that if I take the lead derivative of omega with respect to with respect to x, then this is equal to 0. That's what it means for it to be invariant along the slope generated by some vector. Right? Why is that the case? It's the case because I can write this guy as I x h g plus d I x h acting on omega. Omega is a closed form. So the first term here vanishes. Second term, this is vanishes because omega is closed. This term, the second term, is just minus e squared omega, sorry, e squared h, because omega satisfies this. And d squared is 0 because well, d is non-term. So the lead derivative of the symplectic form along the velocity vector field generated by the Hamiltonian and omega is an invariant. Conversely, if I give you some vector field x and a symplectic form on a manifold omega, you find that the lead derivative of omega with respect to x vanishes. What that means is that we can find the Hamiltonian function of this manifold such that the Hamiltonian equations are satisfied along that flow. Okay? So, conversely, if let's say if V in satisfies the lead derivative with respect to V of symplectic form 0, then we can always find some Hamiltonian such that Hamilton's equations are satisfied along the slope generated by the form. In other words, if the lead derivative omega with respect to B is 0, then you can find an H such that EH is minus I B omega. So show this. Just to be clear, you know how it works. Property 3 is that using the interior product and the symplectic form, we can give a coordinate-free formulation of the Poisson bracket. So to do this, suppose I have two functions. So omega can be used to give a coordinate-free formulation of the Poisson bracket. Suppose I have two functions on base space, let's say F and G, and they're both functions of the Q's and the P's. Those I have some F and a function of the P mu's and P mu's, and another function G is also a function on base space. And now what I'll do is I'll take two interior products of omega. So IXF, yeah, IXG. So I've got function f and g, they all functions on base. Each of these functions generates a velocity vector field in the same way that I defined the velocity vector field. Yeah, right. So each of these guys define a velocity vector field. I then take the interior product, select two forms with respect to the one velocity vector field and the other velocity vector. Okay, you might be concerned about the ordering. Yeah. Show you that the ordering actually used to see this is happening. So if I take the interior product with respect to G first and then F, then it comes with minus. We'll see this. So let's see what happens. So this is the statement that IXF on IXG, or the function of omega with XG. Which is minus IXS dd by the E mu plus the G by the Q in the Q. And this is the one form. So if I contract again with the vector field, this is minus this guy's in here, the by the mu plus G by the Q mu on the F by the E mu, the cubed mu, it means the mu. Sorry, this is a P by Q mu, plus minus the F by the Q mu D by dt, the scalar vector. This is nothing but df by dq mu dg by dp mu minus df by dp mu dg by dq mu. Okay, again, make sure you're comfortable with the manipulations that went into this. So take some time to show this. But this you would recognize as nothing but a Poisson bracket between F and G. So the Poisson bracket between F and G is nothing but two interior products of the vector fields generated by F and G with the symplectic form. And this again gives us a coordinate independent definition of the Poisson bracket that is equivalent to the standard definition when we pick a set of coordinates. And this is clearly minus x g. Okay, so that takes us to everything that I wanted to say. That takes us to the end of the example, illustrated how we can reformulate classical mechanics, classical Hamiltonian mechanics in the language of differential geometry. Phase space is the space in which these two forms exist. So it is identified as a cotangent space, cotangent space on some phase manifold. Now, you can reformulate all of the Lagrangian mechanics the same way, except it would have to take this tangent space. Okay. But this brings us to the end of section on part 2, I guess. Differential calculus manifolds. The next part that I want to just motivate a little bit today. So I'm going to tell you things today that you already well know, and then we're going to substantiate this in the next step. So this is integration of manifolds. So the upshot of the story is the following. You might wonder why you spent so much time talking about forms. Forms are just particular types of tensors that are anti-symmetrizing in particular. You know, why am I distinguishing forms over everything else? I mean, if you were doing geometry, then you really want to focus on tensors rather than forms, right? And you focus on the whole object rather than anti-symmetrization. So why are we focusing so much on forms? You know, apart from things like rewriting classical mechanics, and we can show later that I showed you half of the story that you can rewrite classical electrodynamics in the language of forms as well. Right? You have what you would normally call a four vector, that's what we call derivative of that, you get two vectors equation. I'll tell you about something else just now, and the next couple of lectures called Hodge star operator. Once I tell you about the Hodge star, you will realize that that also tells you the remaining two actual equations. So, okay, great. We can use forms to rewrite classical electrodynamics and classical mechanics. Admittedly, that's half of all physics, but besides that, why else are we talking about forms? The reason we're talking about forms is because forms are the things that you integrate. So, from preschool, first learned about calculus, they told you about integrated functions. You never actually integrated functions. I mean, if you did count the 1000, did something like this, you got kind of wrapped over the knuckles in your test, and you're marking it with going. Right? But don't forget dx. How many you integrate with this way? Oh, you know exactly what I'm talking about. Right? And when I was small, that's there's a reason about this dx. And it is not that I don't know what you're integrating with this thing. It's that this thing, this is a function, is not well defined. Right? F dx, that is a well-defined object, and it is not two things. It is not f dx, it's not an instruction, you get f in this picture. F dx is the thing that you're integrating. It is the integral. Right? And the reason this is true is because this guy is not the same as this guy. Because the other thing that they told you in 1000 is that there's an inherent direction in your integration. You go from left to right, it comes to the positive. You go from right to left, then it comes to the negative sign. And you needed this positive and negative sign to make all the other interpretations that you have, area under the curve, etc., work. It doesn't work unless you have this inherent direction defined with this. Right? Okay. That was the story in one dimension. Then you went ahead in second year and learned about integration. So something like A to B integral from C to G, f of x, y. Again, if you did this in the test, you get that over the line. So and by that stage, you learn that you should put a dx dy, for example. Again, this is a thing by itself. This guy. How do I know this? Well, the way I define this integral, this rectangle, came with an inherent sign convention. Okay? If I had, I could have whatever surface I wanted here. And I took that surface and I broke it up into little rectangles. Right? And then I said I went from A to B, C to C, C to D. Okay. So that gave me some inherent direction. If I went clockwise around this loop, that comes to the positive. If I went anti-clockwise, that comes to negative. Right? That sign convention is built into the fact that this guy here is like a volume. Right? It's like a crossbar convention. So there's an inherent direction implicit in the statement. Technically, it didn't tell you second year, I'm assuming, is that what you were doing was that same wedge product that we've been talking about builds in this first. You went to do 3 dimensions, you had dx, dy, dz. Actually, what you were doing was dx, wedge, dy, wedge, dz, volume form in 3 dimensions. So, underlying all of the stuff that you've already been doing is stuff that we're now making more precise. You've already been working with wedge products. You've already been working with volume forms. Okay. There's one more thing that I want to use to motivate this statement. Sorry, to motivate section of the, and that is the form. When you first learned about integration, they told you about Riemann integration. If you went on again and did analysis, then you would have learned about lots of other integrated measures. There are other famous measures on the Beck measure, etc. But you never actually did an integral, post the first time you learned about integration using first principles. That's because you utilize a really powerful statement known as the fundamental theorem of calculus. If you could find an antiderivative of the integrand, again, not really the integrand, but the integrand. If you could find an antiderivative of this thing instead, then you just evaluate that on the endpoints of the integral. So, fundamental theorem of calculus. I want to be clear about what we're doing. One dimension. Fundamental theorem of calculus says the following. If we have a function f that takes me from some interval a, b to r, then following is true. The integral from a to b of df by dx is f evaluated at b minus f evaluated at a. Again, this minus sign here tells us that there's an implicit direction that we're taking as positive. Okay. So this here goes for us the fact that if we go from left to right, a to b, a equals to b on the real line, then it's positive, but if we go from b to a, then it's negative. Okay. What I want you to take away from this, because everybody knows the fundamental theorem of calculus, that's my point. Point here is I want you to take away the structure. This is the integral of the derivative of something over some line segment, over some space, is equal to that something evaluated on the boundaries of that space. Okay? Yeah. The integral of the derivative of something on some space is equal, the same, is equal to that something evaluated on boundary of space. That is the structure, that's the takeaway message from fundamental theorem of calculus. The one I put in an emphasis on this. See why I put such emphasis on this. Simple one dimension higher. Second year, you would have learned that you've done vector calculus, and you would have learned in your course on vector calculus that there's this thing called Stokes' theorem, right? And there's a variant on it called Green's theorem, but let's just focus on this. In two dimensions, Stokes' theorem says the following. Stokes' theorem says if I have some two-dimensional surface in three-dimensional space, and I have some vector, let's say A, in three-dimensional space. So, given some surface S with boundary two-dimensional surface S with boundary. So let's just use our notation. ds and ds is some loop. So now from the interval of some parameter 0 to t to r main. And the vector field A R3. Then the following is true. The integral, the double integral over the surface S of the curl of A. So the vector, we get a scalar out of this, so we take this curl and we dot it into the unit normal to that surface and integrate with respect to the little surface elements ds, all of which is we've seen before. This thing is the closed integral over the loop that constitutes the boundary of S of A dotted with R, the little line segment along that curve. Again, you've seen this before. This is Stokes' theorem. What I want to emphasize here is that the structure is the same. The integral of the derivative, in this case the curve, of something A is that something A evaluated on the boundary of that region. So Stokes' theorem has exactly the same structure as the fundamental theorem of calculus. But the structure persists if we go one dimension higher. There's a thing called the divergence of Gauss's theorem. Which says that given some region, some three-dimensional region that's a subset of R3, and some vectors with a smooth boundary, and a vector field defined in that region, that's called a vector field B. Then the triple integral over that volume B of the divergence of field B integrated over the volume elements dx dy z is equal to the closed surface integral over the smooth boundary of B of B dot yes. This is what this quantity here is what this is called the class of B to the boundary. Okay, this is the divergence theorem. But again, that's not the point. The point I want you to take away from that is that the structure of the divergence theorem is exactly the same. The integral of the derivative of something over some region is that something evaluated on the boundary of that. The fact that the evaluation is an integral itself is by the by. It's that thing evaluated on the boundary. So all of these fundamental theorems of calculus learned, starting from first year, are exactly the same structure. The integral of the derivative of something, some space, is that something evaluated on the boundary of that. And as you would expect, because we've learned this now, all of these types of derivatives are nothing but the exterior derivative acting on the exterior side. Right? I showed you already. Right here is what we call the gradient. This was the exterior derivative acting on a function f. This was the exterior derivative acting on a one form. That gave me the curve. This was the exterior derivative acting on a two form. That gave me divergence. There are no higher forms and complete forms in three-dimensional space. But here's the thing. These things, I needed this vector to be in R3. Why? Because I can't define the cross product anywhere but R3, except in R7. Okay, I can't define the cross product anywhere but R3, but I can define the exterior derivative anywhere, any method. Okay, so all of these things, all of them, are general can be summed up in our language, and we're going to build to this to expand each of the things we're doing in what's called Stokes' theorem. The generalized form of Stokes' theorem says that if I have some manifold M and some form, some n-dimensional manifold M and some n-1 form omega, then the exterior derivatives integrated over M is just omega evaluated in boundary. And this is it. This encapsulates all of these fundamental theorem of calculus. You just have to pick the form, you just have to pick the dimension, pick the manifold always R3, or R2, or R1. But this is a really powerful statement that sums up all of this. This is called Stokes' theorem, and it is the foundation of what are called Durand homology and homology. Okay. We're going to unpack this stuff in the next couple of lectures. In particular, I'm going to need to tell you, I've already told you this, but I'm going to recap the idea of a manifold with a boundary, this story, and what I actually mean by integrating over a manifold. Okay, and in fact, it's not integration over the manifold, it's what you would have done in first principles integration. You break it up into little things that you know how to calculate areas. Those little things that you know how to calculate areas within this language of general manifold is what's called a chain. So I'm going to show you how you take this guy here and break it up into chains. And technically, a form is something that is paired up with a chain and an integral sign to give you a real number. Okay.